In this video, we will give the definition of a power series and discuss a couple of examples. Up to this point, we only discussed series which contained numbers as their terms. A power series is an infinite sum which contains functions as its terms. Alternatively, you can think of it as a way to generate number series. So let me give the definition first. A power series is the following object. It is the infinite sum with k from 0 to infinity, ck times x to the k. This infinite sum starts off like this. The very first term has k equal to 0. We have c0. And it is multiplied with x to the 0th term, so effectively no x's at all, plus c1x, so that would be x to the first power, plus c2x squared, plus c3x cubed, and so on. In this expression, ck's are coefficients. So they do not depend on x. X is the variable. It can take different values. So for different values of x, you will generate different number series. So what basically happens here is for every numerical value of x, you plug that numerical value into the infinite sum and you produce an infinite number series. So this falls under the general framework of a function. So I want to emphasize that a power series defined in this way is a function. Right? In which sense? Well, if you think of a function as a device, a black box, if you wish, that takes input, so this is the power series, it takes input in the form of the value of x, so it will accept input in the form of the value of x, and it produces output. So the output of a power series is this expression with x replaced by the input. So let's say x is equal to 10. Well, then you write down the infinite sum with every x replaced by 10. So that will be your output. It is a number series. So now you see that just as any function, it takes a number and returns a number series. Now, what can that be? If the number series is convergent, great, then your output is also a number. So that's literally saying that you have a function. If the number series that you obtain by replacing x by the input, let's say 10, by replacing x with 10, you obtain a divergent number series, well, then we will say that such an x lies outside of the domain of our function, given by the power series. Let me give you an example. So, in the general expression for the power series, let us say that all the ck's are equal to 1, starting from the very first ck. All of them are just ones. then what are we looking at is the sum k from 0 to infinity, x to the k. So there are no ck's, we just multiply xk by 1. That's it. And so if you write the first term of the sum, they look like this. They are 1, so that would be x to the 0th, plus x squared, plus x cubed, and so on. Let us think about this expression we obtained. So let us specifically consider the ratios of adjacent terms, like these. So we see that x squared to x is equal to x. And the same goes for x cubed divided by x squared. And so on. It's not hard to check that in this series, all the ratios of adjacent terms are equal to x. And we know what is this property telling us. It's telling us that we are dealing with a geometric series. So for this particular power series, when you just replace all the ck's with 1, you get this expression, which is a geometric series, as we just realized by checking ratios of the adjacent terms. And so this geometric series has ratio equal to x, as we just verified, and its first term, which we know is denoted by a for geometric series, its first term is 1. A is 1. So now we can say a lot about this power series. Now it is a geometric series. It has the ratio equal to x. We can say a couple of things. So first we can say that this power series converges when absolute value of r is less than 1. That's just the convergence criterion for the geometric series. Now, r is equal to x. So we can rewrite this condition as absolute value of x equal to 1. Great. So now we know a lot about this power series. We know when it converges, right? And we know that this when is in fact if and only if. So this power series converges precisely when absolute value of x is less than 1. Now, we also can determine what this power series will converge to. Right? So since it's a geometric series, we can sum it up. So we can say that the infinite sum, k from 0 to infinity, x to the k, is equal to, well, the first term, a, divided by 1 minus r. And this formula holds when absolute value x is less than 1. Great. So not only we were able to determine for which x's this power series converges, we were even able to determine what its sum is equal to. It's equal to this function. Now, you should understand that whereas this function can take the right-hand side here, can take any x, say you can plug in x equals 2, x equals 3, and so on, and you get a nice valid number. On the left-hand side, this expression, this infinite sum, will only converge if absolute value x is less than 1. So this means that the actual meaning of this expression is slightly different from this function, right? So this power series sums up to this function, but only for x's absolute value of x less than 1. So that is the important distinction. Now, in here, we just summed up ckx to the power k. It is often useful to shift this variable x by a constant. So let us give another definition. So we can write down a series like this. Where we'll replace x with x minus a. And so this series now is equal to c0 plus c1 x minus a plus c2 x minus a squared, and so on. So this here defines power series centered at a. So a here is simply a constant. So see what happened? Instead of writing ckx to the k, we replaced x with x minus a, and so we have this shifted power series with new center. So it will be quite useful later on to consider power series with different centers. We'll see that's going to be quite important and nice modification. Okay, so let me give you another example to show the relation of a power series to polynomials. What is the connection between power series and polynomials? Because if you just look at this expression naively, right, it seems that this is almost like an infinite, or maybe it's more transparent if you look at the first definition. So if you look at this expression, this is effectively a polynomial, right? You're just summing up coefficient times power of x, coefficient times power of x, and so on, except that, unlike in a polynomial, you have infinitely many terms. So it's interesting to think about the relation between these power series and polynomials. So let me give you another example. So let us say we have power series centered at, say, 2. So let ck's be 0 for k bigger than or equal to 3. Okay, and let so this defines all the ck's starting from this index. So we have 3 more left. So let's say c0 is 5, c1 is 0, and c2 is let's say 4. Okay, and let us consider a power series centered at a equals 2 with these ck's. So let's see what this power series will look like. Okay, so we have to write the infinite sum, k from 0 to infinity, ck times x minus 2, because a is 2 here, to the power k, right? Except that now all the ck's, except for the first 3, are zeros. So they will all vanish. So all the terms that contain ck's starting from k equal to 3 will vanish, and our infinite sum actually becomes a finite sum. Let's see what it will look like. So here we'll have c0 plus c1 x minus 2 plus c2 x minus 2 squared, right? And there are no further terms because c3 and so on are all zeros. So this is it. This is the entire series. And when we plug in the numerical values we have here, we end up with 5 plus, okay, this term is 0, plus 4x minus 2 squared. Great. So this particular power series with these ck's is nothing but simply a polynomial, 4x minus 2 squared plus 5. Right? And so this is it. If you have a power series which has finitely many terms, you in fact have a polynomial. So this gives you another way of thinking about power series. So power series are somewhat like infinite polynomials. And that is another way to look at them. Of course, there are many questions that remain. So just like in this first example, we would like to be able to determine for which x's a power series converges, and if it does converge, what is the function that it defines? So we will look into these two questions in subsequent videos.